Hello everyone, I'm Byung-Yul Lee from Seoul National University, collaborated with Ok Jung, Professor Jung Choi, and Professor Seung Chan. Today, I want to share our ICCP work, Online Continual Learning on Hierarchical Label Expansion. Online Continual Learning aims to learn sequentially arriving tasks without catastrophically forgetting when data comes in a stream. Upon this setup, various scenarios for realistic online continual learning have been proposed before. However, the hierarchical structure of classes has not been fully explored in online continual learning. By incorporating the setup of hierarchical classification, we suggest new online continual learning setup called hierarchical label expansion. In contrast to hierarchical classification, this setup constrains that only one class from a specific hierarchy level is provided during training, while the network needs to predict the hierarchy branch at inference. Our hierarchical label expansion setup includes two scenarios called single depth scenario and multi-depth scenario. In the single depth scenario, the parent classes are learned at first task and gradually extended to the child classes in subsequent tasks. In the multi-depth scenario, all classes from the previous task are expanded to more fine-grained classes at once. Also, we distinguish single depth scenario into single label scenario and dual label scenario. In the single label scenario, new images are used for the child classes, while the same images are used for multi-label scenario. Our proposed method for this setup is based on previous rehearsal-based approach with class-balanced memory management. Specifically, it first finds the measure class in the memory. For the samples of this class, it computes a measure called lowest importance value, and remove the sample of the least lowest importance value from the memory. Let's talk about the proposed method. It consists of two components: pseudo-labeling based memory management and flexible memory sampling. Pseudo-labeling based memory management is based on class-balanced memory management. That is, we first select the measure class of the memory. One additional condition is that the classes in our memory are hierarchically related to other classes. Therefore, it would be more informative to consider the hierarchy branch not a single class. To achieve this, we predict the hierarchy branch by using the pseudo-labels of selected samples. Then we additionally consider the samples whose predicted classes are from the branch of the major class as the candidates to be removed. After aggregating the candidates, we use the lowest importance value to remove a sample. The second component of the proposed method is flexible memory sampling. It flexibly adapts the ratio of samples from the current data and memory. To realize this, we utilize class-wise time-dependent Bernoulli distribution. If the random variable has the value of 1, then the corresponding sample is included in the training batch. Otherwise, it is rejected from the training batch. By using this, if a sample from the current data belongs to the newly encountered classes, its probability to be included in the training batch is low. Meanwhile, after a certain amount of time has passed since encountering the class, the probability increases. In this way, we adapt the ratio of samples of the current data and memory. This is the experimental result for the single depth scenario. The table demonstrates that the proposed method shows the best final accuracy among the methods on both single label and dual label scenario. Also, graph verifies that the proposed method outperforms the baselines at any time of inference. Lastly, the proposed method also shows the best performance compared to the baselines for multi-depth scenario. These results verify that the proposed method achieved better results for all scenarios than the previous methods. This is the end of the presentation. If you're interested in our work in more detail, please visit our project page. Thank you for listening.